Today we are starting applications of the derivative, and the first one we're going to talk about is extrema on a closed interval. And so what extrema is basically maximum and minimum points. We've talked about the fact that we're going to be able to find them eventually, and now is finally that time. And so the definition of extrema is we're going to let f be defined on some interval I, and it's containing this is an x value c. F of c, the y value when you plug in c, is a minimum of f on the interval I if f of c is less than or equal to all f of x for all x in the interval. Meaning, so this y value is the smallest y value in the area. Okay, maybe not overall, but in the area. And f of c is a maximum of f on I if f of c is greater than or equal to all the rest of the y values in the interval as well. And so I get this little piece like this where the y value is the biggest. Okay, so the minimum and the maximum value of a function on an interval are what we call the extreme values, we say extrema for like multiple, meaning we want to find both the min and the maximum of the function on an interval. So that's just some vocabulary. So we're going to start with the extreme value theorem. So the extreme value theorem says that if f is continuous on a closed interval from a to b, meaning right now, well, we're going to take a step back here in a second, but right now what we're going to do first is try to find the minimum and maximum values in a specific closed interval. So not the entire number line, but just a little piece of the graph. Okay, so that's what we're looking at here. So if f is continuous on this closed interval, so it's just between two different x values, then f has both a minimum and a maximum on the interval. So a lot of times when we're solving problems, we like to have a closed interval because we're guaranteed a min and a max in a closed interval. We'll talk more about this in a minute. So we're going to take a step back and just look at a graph for right now. So we're going to look at the graph of f, which is x cubed minus 3x squared. So at the point 0, 0 here, you can see this is what we call a relative maximum. Okay, it's not the highest point because I have points way up here, and in fact it doesn't have an absolute. Absolute means the absolute largest point in the entire graph. In this sense, this goes up higher and higher and higher and higher. It doesn't have an absolute max, but this 0, 0 here is a relative max, meaning it's the biggest point in this particular area. Okay, it's the top of a roller coaster, right? And so now I can also see that this 2, -4 down here, while not the lowest value overall, right, I don't have an absolute minimum because that would be the very lowest point. Now if this was quadratic and this piece wasn't here and it went up, then this wouldn't be the absolute lowest point, meaning the absolute minimum. But this is the relative minimum because I obviously have y values that are smaller, that are way down here, and they keep falling down and down. So this one doesn't have an absolute minimum, but it does have a relative minimum, the bottom of this valley here. So at 2, -4. So I want us to just demonstrate here for a second. I want to investigate what is the value of f prime of x at x equals 0 and x equals 2. So let's find f prime first. We could just use our power rule here, which is 3x squared minus 6x. So if I plug in 0, f prime of 0, right, I'm just exploring this point here first, is 0 minus 0, which is 0. And f prime of 2 is also, let's see, I put that in, I get 3 times 4 minus 6 times 2, which gives me 0 as well. Okay, so what this means for me is that my tangent lines, right, this is the slope of my tangent line at x equals 0 and x equals 2, are 0, meaning my tangent lines would sit here horizontal. Now this one here you can't really see because it's actually the x-axis, but here my line that would be tangent would be horizontal. So what I'm trying to point out here is that when I get these hills and valleys, then at those places my tangent line is horizontal. So this is going to help us. Okay, so relative extrema, right, which what we just looked at for was just the high and the low in the vicinity occur where f prime of x is either equal to 0, which is what we just saw, or where f prime fails to exist. And we call these numbers, if I plug in a value c and I get f prime of c is equal to 0, or if f prime of c fails to exist, then we say that c is a critical number, okay? So if I get, I should really have f prime of c is equal to 0. So here at c, right, my tangent line is horizontal. I get a picture that looks like this. And, or over here, remember, f prime of c fails to exist here at this point because I have this sharp bend, right? This is an absolute value graph, which is continuous but not differentiable at the sharp point. But it's still, obviously in both of these cases, I have a relative, at least relative, maybe absolute, depending on the rest of the graph, maximum point here and here. And so when I find a c value that makes my f prime equal to 0, then my picture looks like this, or I guess it could also look like this, right? Where my tangent line is down here. But my absolute, or my relative, I should say, because we don't know the rest of the graph, we'll say relative max or relative mins occur where my tangent line is horizontal, which means where f prime of x is equal to 0. Or it's at the sharp points, right? I could also draw one that looks like this, which is the min. And these are places where the derivative fails to exist. So if I'm trying to find the highest and the lowest points on my graph, then I find where the first derivative is either equal to 0 or where the first derivative is equal, not that it's equal to anything, that it fails to exist. Okay? So any value c that makes that happen, if f prime of c is equal to 0 or if f prime of c fails to exist, then we call c a critical number of f. Okay. So I've talked about this already, but I wanted to formally just define it. I've thrown around these terms and sort of explained them. But the absolute extrema is the highest or lowest value in either an interval, if I'm just looking at a snapshot, or on the entire number line. Now every thing, if I have a closed interval, then I always have an absolute max and an absolute min because I'm only looking at a snapshot of my graph. If I'm looking on the entire number line, not every function has an absolute max or min. We're going to look at that in a second. Relative extrema means it's the highest or lowest value in the local area. Now, oftentimes when we get to the first derivative, we talk about things just being relative extrema until we're certain that it's the absolute extrema. All right, so we're going to go back to our snapshot. Okay, so we're going to start out with finding extreme values in a closed interval, meaning not on the entire number line, just in between a specific x to different x values. Okay, so what we do first is we find the critical numbers of f in AB, meaning I'm going to find all the places where my f prime is either equal to 0 or my f prime does not exist. Then we're going to take those critical numbers, those values that make my derivative 0 or make it undefined, and we're going to plug them into f and see what we get out for y values. Then we're going to take the endpoints a and b and plug them into f, okay? And we're going to see what y values we have. And then my last piece is then, once I do that and I have the list of all my y values, the critical number with the smallest y value is a minimum, and the biggest one is the maximum. Okay, so we saw that the highs and lows, right, these come at places where my derivative is equal to 0. But we evaluated the endpoint because my high and low could come on the endpoint just about the way I cut the graph, right? So here, like I have this maximum point sitting up here, but if I'm only looking between these, then maybe my max in the interval would only be right here on the end. So we check the endpoints because it might just be the way we cut the graph that my minimum or my max values come on the ends of my interval. Okay, so let's look at this example here. So we're going to find the extrema, meaning I'm going to find the relative min and max, or actually in a closed interval I'm guaranteed a min and a max, okay, because my endpoints are included. So since I'm just looking at a snapshot of my graph, I'm going to find the absolute extrema in this case. So f of x is 3x to the fourth minus 4x cubed. All right, so my instructions tell me to first find the critical numbers of f in AB, which means I need to find f prime. So I have f prime of x, which is equal to, so I'm just going to use my power rule here. I have 12x cubed minus 12x squared. So I'm going to find places where f prime is equal to 0. Now, I can also find critical numbers where f prime fails to exist, but with a polynomial function, I'm not going to have a place where f prime fails to exist. F prime will fail to exist if I have a rational function or if I have a bottom piece of my denominator here. Okay, so I'm going to set this equal to 0. So factoring is my friend again, and I can factor out a 12x squared, which is common. So this leaves me with x minus 1. So I get 0 equals 12x squared, or 0 equals x minus 1. I'm using the zero product property, right? So this times this equals 0 means that this is equal to 0 or this is equal to 0. This one gives me x equals 0. This one gives x equals 1. Now both of my critical numbers, right? These are my critical numbers. I'm just going to call them CN for short. Okay? They're both in my interval. They're between -1 and 2. If I'd have, for instance, found x equals 3, then I could throw them out in this particular case because it's not in my interval, and I don't really, it's outside of where I'm looking. So now, did that. Step 2 tells me to evaluate f at each critical number. So I'm going to take f and plug in 0, and then I'm going to take f and plug in 1. So if I plug in 0, I'm immediately going to get out 0. And if I plug in 1, then I get 3 times 1 minus 4 times 1. So really I get 3 minus 4, which is -1. All right. So now I also need to evaluate my values on the endpoints because it may just be a product of how I cut the graph, right? This is a polynomial function with x to the 4th, so it probably, well, not probably, it does have an end behavior that looks like this, right? So if I was looking at the entire number line, I would never have an absolute maximum, but I'm going to just cut the graph off, and I'm just going to look between -1 and 2. So we will have an absolute maximum. All right, so then I'm going to evaluate at f of -1. F of -1 will give me, so I plug in -1 here. When I raise it to the 4th, it'll become +1, so I get 3. And then this will become +4 because I raise -1 to the 3rd power, which remains -1, and then I multiply it by -4. So I end up with 3 plus 4, which is 7. Okay. So now I'm also going to do f of 2 because that's my other endpoint. F of 2 is 3 times 16, because 2 to the 4th is 16, minus 4 times 8. All right, so I get, let's see, I get 48 here, minus 32, which is 16. So I've evaluated, these are my critical numbers, these are my endpoints, and now I'm going to look, okay, well, what's my biggest y value? Well, my biggest y value is right here, right? So my maximum occurs at x equals 2, and it's 16. And my minimum comes at, so this is my min, and this is my max in the interval. Okay, so I have the graph here. Right, so I've got the domain restricted, so we're only seeing it, right? Just between them. If I took the domain restriction off and I graphed it, right, these would both just go up and up and up in both directions because I have an x to the 4th, right, which has the same matching end behavior. So you can see my minimum point down here, that looks about right, is at 1, -1. Okay, so that's where my derivative was 0. If I put in my tangent line is horizontal at that place, right? If I drew it down here, it would be straight across. And then my maximum point comes on the right end point. See, because of the way I cut the graph, it just cuts off right there, right? My normal graph, if I didn't cut it off right there, it would just keep going up and up and up. So I would never have a true maximum because there wouldn't be a stopping point. But since I'm stopping the graph and looking at it at 2, then that's the highest piece, right? Because I don't have any Like this piece over here is definitely lower, and so I come up here to this place, and that is, well, I have it undefined because I don't have the interval in there, but it's at 216. You can see from my x value being at 15 here, so that's 16. Okay, so I'm just looking, I'm not looking on the entire number line, I'm just looking at a piece of the graph and looking. So when I'm only looking at a piece, I'm guaranteed a max and a min of absolute, right? It's the very lowest point and the very highest point. All right. So let's look at, we're going to try to find the absolute extrema of the function in these different intervals. Okay, so f is 3x minus 1 in each interval. So I have the graph here, right? This is a linear function. And I'm going to put some points on here. This is the point 0, negative 1, and this up here is the point 2, 5. All right, now in my first one, so let's look at, so the first thing I'm supposed to do is find where f prime is equal to 0, or it doesn't exist. F prime of x is equal to 3, and 0 does not equal 3. So essentially what this means is I get no critical numbers. If you look at my graph, right, I really don't have, right, my derivative looks like 0 at places that look like this, right? I don't have that turnaround behavior. This is a straight line. So my min and my max will occur just from the way I cut my graph. So I don't have any critical numbers. So the first one interval I'm going to look at is between 0 and 2. I'm using the closed bracket, so that means I'm on a closed interval. So that means I'm guaranteed a min and a max. And so you can see from my graph, if I plug in f of 0, also up here I get negative 1, right? That's that point right there. And if I plug in 2, my other endpoint here, then I get 5. That's this point up here. So I have no critical numbers, and so that means that this is the min and this is the max. Okay? So I'm guaranteed a min and a max in a closed interval where the endpoints are also included. Now this one here, getting you a little used to interval notation here, this means I'm including the 0 but not including the 2. So that means this point up here that I have filled in is really not filled in. So basically my picture looks like this, right? This one down here is filled in. It's 0, negative 1 without drawing the whole thing. Up here I have the point 2, 5. So this is just a little snapshot of it. So based upon this picture, I am going to have a minimum, right? This will be my minimum, but I don't have a maximum because the biggest point comes here, but it's not included. So this one where we're not including the 2 has a min but no max. So I'm trying to reinforce. I only have a min and a max when I include both endpoints, where I'm guaranteed a min and a max. I could still have a min and a max depending upon what my graph looked like, but I'm only guaranteed one when the interval is closed, meaning it's including the endpoints. So here I don't have the 2 included, I have a min but no max. Here, going the opposite direction, right, if my graph looks like this, that means I have this going on. So this time I'm including the 2, so I have this 0.25 up here. This one down here is 0, negative 1. This picture, right, I'm still just drawing a picture of this up here. It has a big point, it has the maximum point on the interval, but no minimum point. Okay? So again, not guaranteed a min and a max in a closed interval unless it's a closed interval. So this side is open, this side is closed. I have the max but no min down here because the smallest value would occur right here, but it's not there. And then lastly, my last interval, both my 0 and my 2 are not included. So basically I have a picture that looks like this, where my maximum would occur up here, my minimum would occur down here, but neither one of those endpoints are included. So this one has neither, right? This one has a max only, and this one has a min only. So I'm just trying to re-emphasize, I'm only guaranteed a minimum and a maximum in an interval if it includes both of the endpoints, if it's closed. All right. So let's do a little practice. Most of the ones that I did so far are pretty basic with the derivatives. This time we're just going to find the critical numbers of f. Okay, so that means I'm trying to find where my derivative is either equal to 0 or f prime does not exist. So I'm going to find f prime first. So f prime, again, I have a rational function, which means I'm going to need the quotient rule, which tells me I'm going to have the bottom times the derivative of the top, which the derivative of 4x is 4, minus then the reverse. I have 4x times the derivative of the bottom, which is 2x, and then I have x squared plus 1 quantity squared. All right, so let's clean up the top again. We never ever multiply out the denominator here. We always just leave it. But we will clean up the numerator because I want to know where f prime is equal to 0. So I multiplied through the 4, and I'm going to get 4x squared plus 4, and then this will be minus 8x squared. All right, so f prime of x, let me just clean it up one more step. I can write this as, these are like terms here and here, right? So I have negative 4x squared plus 4 over x squared plus 1 quantity squared. The first thing I want to know is where is f prime equal to 0, right? That's my easiest one usually I go for first. F prime of x is equal to 0. When I set this equal, you're going to see me kind of omit this step after this process because the first step is to multiply both sides by the denominator because I need to get this out. And when I do that, every single time I do that, I get 0 on this side and I end up with the numerator on this side. Okay, so I'm pretty much going to omit this step from this because this happens every time. I'm just going to end up with the numerator equal to 0 because I multiply both sides by the denominator. This side cancels, turns to 1. This side becomes 0. So now I need to know where this is true. So I'm going to move my 4x squared on this side. I'm going to divide both sides by 4, get 1. And I get x equals plus and minus 1. So I have found where f prime of x is equal to 0. So I have f prime of 1 is 0, and f prime of negative 1 is 0. That means 1 and negative 1 are critical numbers of f. All right, so then I want to also find if I have f prime of x where it fails to exist. And it will fail to exist when I have 0 in the denominator. So that's what I'm going to look at. Can I make the denominator 0? So I have x squared plus 1 squared equals 0. Again, this is kind of an algebra step you're going to see me omit from here on out. But whenever I have something to a power, the first thing I'm going to do is undo the power. So I'm going to take the square root of both sides, right? And so I get x squared plus 1 is equal to 0. You're just going to see me, for the most part, drop the power because this happens every single time. So then I try to do x squared equals negative 1, and I don't get, there's no solution here. So there's no places where my first derivative fails to exist. So my only critical numbers come from where f prime of x is equal to 0. All right, so one more, extrema on a closed interval. So we're going to find the min and the max, and they're guaranteed to be 1 because I'm in a closed interval, meaning I'm including negative 1 and 2. So I'm going to find f prime of x. F prime is 3x squared minus 3 halves times 2, right, because I'm just using my power rule, times x. So f prime of x is equal to 3x squared minus 3x. I don't have any denominator, so I can rule out the fact that f prime of x will fail to exist somewhere. So 0 is equal to, again I'm going to factor. I factor out the common 3x, and I get x minus 1, which gives me x equals 0 from setting 3x equals to 0, and x equals 1 from setting x minus 1 equal to 0. Okay, so these are both in my interval, so this is good. So I'm going to evaluate f of 0 and f of 1. Those are my critical numbers. And then I'll evaluate my endpoints next. So when I plug in 0, I get out 0 because I have 0 in both. when I plug in 1, I'm going to get 1 minus 3/2, and I end up with negative 1/2 here. So now the endpoints, right? Because my min or my max could come on the endpoints just because of the way I cut my graph off. So I'll do f of negative 1 here. When I do that, and I raise negative 1 to the third power, I end up with negative 1, and then minus 3/2. Because when I square the negative 1, it'll become positive. So I just end up with negative 1 minus 3/2, which is negative 5/2, or negative 2.5 for all those of you who are obsessed with decimals, but you should really write the improper fraction. Right? And then my last endpoint is 2, and so 2 cubed is 8, minus 3/2 times 2 squared, which is 4. So my f of 2 here is equal to 8 minus 12 over 2, which is really 8 minus 6, which is 2. All right, so let's see now. So I have negative 2.5 here. That seems to be my smallest y value. So that's my minimum. And then I get 0 here, and 2 is bigger than that. Right? And this one's negative, so this means that f of 2, which is 2, this is my maximum on the interval. Right? This is an x cubed, and so I know with its end behavior it should look like this, right? So if it weren't on this closed interval, I cannot say these are really both absolute. They're the absolute lowest and the absolute biggest in that interval. And so because I'm going to have this end behavior, this one's shooting off into positive infinity and this one's shooting off into negative infinity, I would definitely not have an absolute max and min on the entire number line because of this behavior. But if I just cut out a piece and look at that, then I can. All right, so we can't leave out some trig examples, so let's do a trig example. So we have f of x equals x minus 2 sine of x in the interval from 0 to 2 pi. So we're on a closed interval. So to find our critical points, we're going to do the derivative. So f prime of x equals 1 minus 2 cosine of x. And now we can set our derivative equal to 0 to find our critical numbers. I'm going to add the 2 cosine of x to the other side. I get 2 cosine of x equals 1. So cosine of x equals 1/2. All right, so we can figure this out. We know that there are values of x that give us 1/2. That would be multiples of pi over 3. So cosine is positive in the first quadrant and in the fourth quadrant. So that means 5 pi over 3 as well. All right, so here's our critical numbers. So I'm going to rewrite the function because we're going to have to move down the page. Okay, so now we need to do the endpoints. So we're going to have f of 0 and f of 2 pi. Oops. And then also f of pi over 3 and f of 5 pi over 3. There, now we can fit it all in there. Okay, so when I plug in 0 here, I get 0 minus 2 sine of 0, and sine of 0 is 0, so this whole thing is just 0. All right, so if I put in 2 pi, I'm going to get 2 pi here, and then sine of 2 pi is 0 again, so actually I just get 2 pi here. So that's, we'll say, approximately 6.28. All right. Let's try pi over 3. So pi over 3 would be pi over 3 minus 2 times the sine of pi over 3, which is square root of 3 over 2. So here my 2's will cancel, leaving me with pi over 3 minus the square root of 3, which my calculator tells me is approximately negative 0.684. We do need to approximate these so we know which one's bigger and which one's the smallest. So right now, 2 pi is in the running for biggest, and pi over 3 is in the running for smallest. So we still have 5 pi over 3 to try. So we get 5 pi over 3, and then minus 2 times, this time, my sine of pi over 3 is negative. So this will be negative square root of 3 over 2. So this ends up being 5 pi over 3 plus the square root of 3, which when I approximate this one, it is approximately 6.97. Okay, so 5 pi over 3 is my winner for maximum. It's got the biggest value, y value, in the interval from 0 to 2 pi. And then my smallest is the only one that's negative, which is my pi over 3 is my minimum. And these are absolute because they're in the closed interval. Right, so once again, right, if I didn't have a closed interval, this would just keep repeating and repeating, so I would have multiple, right? So we can't really say it would be an absolute min or a max if we didn't have this interval. So, all right.